Welcome to a screencast on an introduction to atomic structure. Let's start out with the fundamental particles of elements, the building blocks of the elements, which of course are atoms. And almost certainly from a previous chemistry class or just general knowledge, you remember that atoms are made up of even smaller particles called protons, neutrons, and electrons. Now the protons have a positive charge, the neutrons have a neutral charge, and those two constituents of atoms are in the nucleus. They make up the nucleus, and that's where almost all of the mass of an atom resides. And here's a table showing characteristics of the various subatomic particles. Protons are in the nucleus. They have a charge of 1.6 times 10 to the minus 19th coulombs. Unit charge we often refer to as just +1. It has a mass of a little over 1 atomic mass units, or AMU, or if you prefer its mass in grams, 1.67 times 10 to the negative 24th grams. Similar idea for the neutron, also in the nucleus, 0 charge, mass a little over 1 AMU, fairly similar mass to that of the proton, just a little bit more. And then electrons, we'll talk about next, are outside the nucleus. Same charge as a proton, but opposite, it's negative, and much, much smaller mass. Okay, so let's talk about the electrons a little bit. They have a negative charge, they surround the nucleus, and they make up almost all of the volume of the atom. So if we looked at kind of a cartoon version of a typical atom, it has a nucleus made up of protons and neutrons, and then it's surrounded by electrons. We often think of them as being in electron shells, not really orbiting in circles like it's shown here, but we often do this as kind of a simplistic version. And so the electrons are in electron shells, and they surround the nucleus, and they make up almost all of the volume of the atom. They move around really fast, and they take up the space that corresponds to the volume of the atom. Now, one thing that's kind of worth noting just in terms of scale, a typical atom is going to have a diameter in the ballpark of 10 to the minus 10th meters. And typical atom's nucleus is going to have a diameter in the ballpark of 10 to the minus 15th meters. So about 5 orders of magnitude, or a factor of 100,000 smaller for the nucleus compared to the atom itself. And just to put this in perspective, if we could take an atom and expand it to be the size of a typical football stadium perhaps, then the relative size of a nucleus in that atom would be about like having a blueberry, one blueberry in the middle of this big stadium, which is representing the volume of the atom. So very, very, very small nucleus by comparison to the size of the atom, but nonetheless, almost all of the mass, 99.9+% mass, is in the nucleus. Okay, well, let's look a little more at what we can get from, in terms of atomic structure, from the periodic table and some of the values given for each element on a periodic table. And let's use the example of oxygen, symbolized by O. And if we look at its periodic table information, there's an 8 in the upper left-hand corner and a 16.00 below that. And the 8 is what's called the atomic number, and it represents the number, or it specifies, I should say, the number of protons and also the number of electrons in an atom of that element. The symbol we sometimes use for atomic number is Z, and so an atom of oxygen has 8 protons and 8 electrons. So atomic number tells us the number of protons and electrons. Now, here's again the cartoon version of an atom of oxygen. 8 protons in the nucleus, 2 plus 6, a total of 8 electrons in the surrounding electron shells. And for an atom, the number of positive charges, in this case 8, and the number of negative charges, in this case 8, are equal, and overall the atom is neutral. And this is going to be true for an atom of any element, except the numbers will be different. An atom of a different element will have a different number of protons and a different number of electrons than oxygen. Now, the other thing we should consider is something called the mass number. It's symbolized by A, and the mass number specifies the number of protons and neutrons, the total number of protons and neutrons in a particular type of atom of a given element. Now, the number listed below oxygen, 16.00, is called the atomic mass. We'll talk in a little more detail about that in a moment. It is not the same as a mass number, but it's sort of close-ish to that. So we'll talk about that in just a little bit of detail, but note that the 16 for oxygen, 16.00, is atomic mass, not exactly mass number. So for oxygen, it's always going to have 8 protons, always going to have 8 electrons if it's an atom of that element. And for a particular type of oxygen atom that has a mass number of 16, that, and by the way, we can represent that as O-16 for oxygen 16. We can also write it as O with a superscript to the left of 16 to represent the mass number, and then 8 as a left-hand subscript. It's a little redundant, but it emphasizes that the atomic number of oxygen is 8. And since it's redundant, we typically or often will leave it off. So we can also write the symbol for an oxygen atom with mass number 16 as O with only the superscript 16. And all of these three symbolic representations mean the same thing. Now, an oxygen atom with a mass number of 16 has 8 neutrons because the total number of protons and neutrons in an oxygen atom with mass number 16 is 16. 8 of those are protons, and 16 minus 8 leaves us with 8 that must be neutrons. So if we know the mass number, we can subtract the number of protons, which is the atomic number, from the mass number. That always will tell us the number of neutrons. So, how many protons, neutrons, and electrons are in an atom of bromine 80? And if we look at the periodic table and find bromine, we'll make it a little larger so we can see easily. And 35 and 79.90 are the numbers shown on the element symbol, or with the element symbol for bromine. And of course, 35 is the atomic number, and that means an atom of bromine has 35 protons and 35 electrons. Now, the mass number is 80 for this particular kind of bromine, and what that means is there's 80 total protons plus neutrons, of which 35 are protons. Therefore 80 minus 35 gives us 45 neutrons. And an atom of bromine 80 will have 35 protons, 35 electrons, and 45 neutrons. Now, how would we describe a typical carbon atom? Well, using the things we've talked about just a moment ago, carbon has an atomic number of 6, an atomic mass of 12.01. We can write a symbol of a typical carbon atom as C12 or C12, showing it this way. It's going to have 6 protons and 6 electrons because its atomic number is 6. And a typical carbon atom will have a mass number of 12, very close to the 12.01 atomic mass. And so it's going to have 6 protons, 6 neutrons, and 6 protons, 6 electrons, and 12 minus 6, which is 6 neutrons. And it might look something like this, with a red sphere here representing a proton, a blue sphere representing a neutron. We have 6 of each in the nucleus. And then yellow spheres representing electrons. We have 6 of them surrounding the nucleus in electron shells. But Some carbon atoms look like this. And if you weren't paying attention, let's go back a moment. Here's carbon-12 with 6 protons and 6 neutrons. Pay close attention to the nucleus. And there's one more neutron in this carbon atom. And it still has 6 protons, so it's still carbon. But it has 7 neutrons. And then, of course, it has 6 electrons if it's a neutral atom. So this is still carbon, but it has more neutrons. Therefore, it has a heavier or larger mass. We can write this as C13 because there's 6 plus 7, which is 13 total particles in the nucleus. And if we kind of continue with this train of thought, we notice that there's other carbon atoms that look like this. And this one, if you count carefully, has actually 8 neutrons. So this kind of carbon atom has 6 protons, 6 electrons, and 8 neutrons. In other words, it's carbon-14. 6 plus 8, 6 protons plus 6 neutrons, adds up to 14 for the mass number of this carbon atom. Well, all of the 3 atoms that we just talked about, carbon-12, carbon-13, and carbon-14, are carbon atoms, but they are what are called isotopes. These are atoms of the same element that have different numbers of neutrons, therefore they have different masses, and isotope is the term chemists use to describe these kinds of atoms. Iso means same, and they are atoms of the same element, but they have different masses. So carbon-12, carbon-13, and carbon-14 are all isotopes of carbon. And in fact, carbon has other isotopes as well. Okay, now let's go back to this thing we mentioned before, atomic mass, that was noted as not quite the same as mass number. So what is atomic mass? Well, atomic mass is the average of the masses of the elements naturally occurring isotopes. So if you go to nature and grab up a bunch of carbon, some will be carbon-12, some will be carbon-13, some will be carbon-14, and others as well. And if we average out the masses of the isotopes of that element according to their natural abundance, we'll get the atomic mass value, which is reported on the periodic table underneath that element symbol. Now, this might be easiest to see by example, so let's do chlorine because this one has 2 predominant isotopes. It has the isotope chlorine-35, which has a mass for one atom of 34.969 AMU, and 75.76% of the naturally occurring chlorine is chlorine-35. Similar idea for the remaining 24.24%, that's chlorine-37. Each atom of chlorine-37 has a mass of 36.966 AMU, and an AMU is the symbol we use for atomic mass unit. So this is an atomic scaled mass unit, and it's relative, and so we have the atomic mass unit values for the mass of these 2 isotopes of chlorine and their relative abundance. And if we take the relative abundance of the chlorine-35 isotope, which is 75.76%, or 0.7576 as a fraction, as a decimal, multiply that by the mass of a chlorine-35 atom, and then take 24.24% as a decimal of the 36.966 mass chlorine-37 isotope. That gives us an average mass of the naturally weighted average of the naturally occurring isotopes of chlorine of 35.45 AMU, and if you look on the periodic table, that's the value that's listed. Now notice that lots of chlorine atoms have mass number 35. Not as many, but still quite a few, have mass number 37. That gives us this average. If you were predicting mass number of chlorine atoms, you'd predict they'd be in the ballpark of 35 or 36 or 37 or so. We can't necessarily predict, we can't at all predict the abundance from the value here for atomic mass. It would only give us a ballpark idea of what would be, most of the naturally occurring isotopes of that element. And that's it for our introduction to atomic structure.